So the last bit of this story about limiting reactants deals with percent yield. And percent yield is a way to kind of gauge how well the reaction was performed. And so with percent yield, there are two components. We have the theoretical yield. And again, this is the amount of yield if the reaction went 100% to completion. So if your reaction went perfectly, this is how much you would get. And then the other one is the actual yield. Which is the amount of yield you actually got produced from the experiment. So if you go into the lab and perform the experiment, theoretical yield tells you how much you should get. Actual yield tells you how much you actually get. And so in textbook problems, actual yield is either given to you directly or indirectly. So when you're given a problem involving percent yield, if you're looking for percent yield, it'll give you the actual yield in the problem. It'll say we produce this much of a certain product. Indirectly means it may give you the percent yield and ask to calculate how much actual yield was actually produced. And so the actual yield is something that's going to be given to you again directly or indirectly. And so the way we find percent yield is actual over theoretical times 100. And so your theoretical, or excuse me, your percent yield shouldn't be over 100% because that means you made more product than you should have based on the calculation. So the theoretical yield is always determined by the limiting reagents. The actual yield is what you get from the experiment. So you can't produce more yields than what you've calculated is the maximum you can produce. So if your theoretical yield is 50 grams and you produce 60 grams of product, something is wrong about either your calculation or you've done an impurity in your experiment. So your percent yield should never be over 100. That's a bad sign if it's over 100. Now it'll never, in reality, it'll never be actually 100. It'll be close to 199%, 98%. But even if it's less than 100, like 70% is okay for some reactions. You even have some that are 50%, 30%. And especially if it's a new type of reaction that you're trying to make or trying to create, you may have a very low percent yield. But the red flag is when you have a percent yield that's over 100%. You should investigate think of why it's over 100%, because that's a bad thing. So now we're going to look at some examples involving percent yield.
Up early lately.
I woke up early. I just like
All righty, let's continue. So here's our first example. We have a reaction involving 55 grams of hydrogen with 120 grams of nitrogen produces 85 grams of ammonia. What's the percent yield of the reaction? So again, this 85 grams of ammonia, this is the actual yield of the problem. So we don't want to use this number until we find the theoretical yield. So you don't touch the actual yield until you're ready to calculate the percent yield. And a lot of students, they'll get confused. They'll start using this number, the actual yield, right away. You only use it once you're ready to calculate percent yields. We'll just leave it to the side for now, and we look at the other bits of information. So we have 55 grams of hydrogen and 120 grams of nitrogen. So that's our amount of each reactant. So what we have to do is determine the limiting reagent, and then from there we can determine the theoretical yield. Now to balance this equation, you see that hydrogen and nitrogen are unbalanced, but you'll notice here that the hydrogen is a subscript of 2. Hydrogen over here is 3. So it's best to balance the hydrogen first because it's an even-odd combination. So here hydrogen has 2, this hydrogen is 3. The common multiple between 2 and 3 is 6. So we'll put a 3 here and a 2 here. And so when we do that, we see that all the elements are balanced. Now we got to calculate how much product is produced by each reactant. So we'll start with hydrogen. 55 grams H2. We draw the train tracks. We're going to divide by its molar mass. And the mole ratio here is 3 to 2, so 3 moles of hydrogen, 2 moles of ammonia. Again, on the left side of our train track, we're starting with hydrogen. 1 mole of hydrogen is on top, so that means that the moles of hydrogen go on the bottom. And the moles of ammonia go on top. Now we see how much ammonia is produced by hydrogen. And we get 18.33 moles of ammonia. Now we do the exact same thing for nitrogen. And here we're starting with 120 grams of N2. Do our train track. First step, we convert to moles. Now here you see mole of nitrogen is on top. The next step is our mole ratio. 1 mole of nitrogen gives 2 moles of ammonia. So nitrogen goes on the bottom. Ammonia goes on top. And now we can determine the amount of moles of product produced by nitrogen. And we get 8.57. So this tells you that nitrogen is the limiting reactant because it produces the fewer moles of product. Doesn't mean it's always going to be the limiting reactant. It just means in this particular question, it's the limiting reactant. So then we're going to take and convert this to mass.
We get 145.7 grams of ammonia. So now our percent yield is going to be the actual, which is 85, divided by 145.7. That's our theoretical times 100. And we get about 58.3%. So again, this 145.7, this is the theoretical yield. So when we're doing these problems, you should see a very similar repeat pattern. We're doing the same thing, but we're just changing the numbers. So here we have this combustion reaction. We have butane plus oxygen gives us CO2 and H2O. If we have 5,300 grams of CO2 are produced when we react 1,500 grams of butane with 9,500 grams of oxygen gas, calculate the percent yield. So our reactants are 1,500 grams of butane, 9,500 grams of oxygen gas. What's the percent yield? So again, this 5,300 grams of CO2, it says are produced. So this tells you it's the actual yield. So since it's the actual yield, we don't worry about this until we're ready to calculate the percent yield. And so again, what we're going to do is we're going to determine the moles of each moles of product produced by each reactant. So we're going to start with butane. We have 1,500 grams of butane. Let me draw the train track. Again, the first step, we're going to convert it to moles, so we divide by the molar mass. That gives us moles of butane. Then the mole ratio is 2 to 8, so 2 moles of butane gives us 8 moles of CO2. And we get about 103.4 moles of CO2. Now we do the same thing for O2. So we're starting with 9,500 grams. First step, we're going to convert to moles. Here the mole ratio is 13 to 8, so 13 moles of O2 gives us 8 moles of CO2. And we get about 182.7 moles. So here in this example, butane is the limiting reactant because it produces a fewer moles of CO2. So then we're going to take the moles of CO2 produced by the limiting reactant and convert it to mass. And we get 4549.6 grams. So this is the theoretical yield. And so if we calculate the percent yield, we get that it's 116%. So whoever did this chemical reaction did something wrong, because you see we have over 100% yield. So they would need to go back, look through their notes or observations to see what might have caused them to get a higher yield than expected. Let's get to, yeah. So the first two examples we did were straight up, what's the percent yield? It gives us the amount of actual yield. It gives us the amount of reactants. And it says, hey, what's the percent yield? The other type of problem you can get is that it gives us the amount of reactants. And it says this reaction has a, in this example, a 60% yield. What is the actual yield of the reaction? So maybe you're doing a reaction, you read in a paper or an article that this reaction has a 60% yield. You start with this amount of each reactant. You want to know how much actual yield you'll get. And so the first thing we need to do is to determine the theoretical yield. So again, this percent yield, we're not going to use until the end once we've determined the theoretical yield. Because if you remember from earlier, percent yield equals actual or theoretical times 100. So if we know the percent yield, which is given to us, and we can calculate the theoretical yield based on the limiting reactant, then we can determine the actual yield. So again, we're not going to use this percent yield until once we determine the theoretical yield of this reaction. So again, we got to do the same steps. We got to find out the moles of product produced by each reactant, and also which one is the limiting reactant, so that we can determine the theoretical yield. So we'll start here with P4, 27 grams. First step is to convert it to mass. Second step is to convert it, or excuse me, first step, convert it to moles that we want. Second step is to convert it to the moles of the product. So we're going to go mass to moles and then moles to moles. And phosphorus is the only non-metal on the periodic table that is tetraatomic. So now you look here, the mole ratio between P4 and Pi3 is 1 to 4. So we have 1 mole of P4 on the bottom. 4 mole of Pi3. Get 0.871. Now we do the same thing for I2. First step, we're going to convert it to moles. Again, iodine is a diatomic element. And then here you see the mole ratio is 6 moles of I2 to 4 moles of PI3. So I2 goes on the bottom. We get 0.178 moles of I2. Double check. So here you'll notice that in this example or this question, I2 is the limiting reactant. And so now we need to convert the moles of I2, or excuse me, moles of PI3, not I2, to grams. So molar mass. One mole. And we get 73.3 grams. And again, this is the theoretical yield. So now we have the theoretical, we have the percent yield, we can calculate the actual yield. So actual yield equals percent yield divided by 100 times actual or theoretical yield. So basically we're going to take 60% of 73.3. Now remember, 60%, you got to get rid of the percent, so that's why we divide by 100, so we get 0.6 times 73.3. And we get 44 grams, or I should say 44.0 grams of PI3. So that's what the actual yield would be if you do this experiment. It's supposed to get a 60% yield reaction. If you were to start with these amounts of reactants, you would produce an actual yield of 44 grams. So again, what we're doing in each step is first we found the limiting reagent by converting the moles of each reactant into moles of product, seeing which one produces the fewer moles of product. Once we identify the limiting reagent, we can calculate the theoretical yield. And then we can calculate either the percent yield or in this case, the actual yield.